The last class we have introduced the do loops and stated that the general structure of do loop is do blank statement number blank dummy variable I, its initial value, its final value, and its step I step, and the statement number. If we use a statement number 99, then all the lines starting from just after the loop do to number 99 will be repeated for all the values of the dummy variable. The repetition will continue up to the statement number given over here, inclusive of the line itself. This is the general structure of do loop. Today I shall consider few examples or few simple programs which utilizes the concept of do loops. First problem is to calculate the sum of first n natural numbers. So we are provided with sum for beforehand, and we calculate the sum of this, and then Sn square, which is the sum of the squares of the natural numbers, n square and Sn cube I want to calculate these three things in a single program. So we start our program like this: 1 2 2 5 6 7. First line is to read the n. Then we are to initialize these sums. So we first we want to perform this calculation in integer mode. So I like is equal to 0, is2 is equal to 0, and is3 is equal to 0. Actually, the naming we have named the variable in such a way that it stands for the Sn. So its name is is in integer mode sum. This is is2 sum square, and this is is3 sum cube. Then we write do blank I is equal to 1 comma n in steps of 1. Then come to is is equal to is plus is2 is equal to is2 plus I double star 2, and is3 is equal to everything has been done. So oh sorry, I forgot to put the statement number. So we like 97, I is equal to 1 to n. So in the column star comma star in is2 is3 stop end. This is the basic program. Now let me explain how does the program work. First, we initialize all these things. So this is the initialization part. This is very important. The initialization in proper place is very important. If one of the statement were put within the do loop, the entire result will go wrong. So first what it does, it takes I is equal to 1, then it produces this sum. So initially is was 0, so it adds 0 plus 1 is 1. Now at the first stage is is 1, and is2 is similarly 0 plus 1 square is also 1, and this is 0 plus 1 cube is 1. Since it is written 97, this 97 statement number has been attained, so it then returns to here and assumes the second value of I, that is I is equal to 2. And in this case it adds 1. Is was 1 in the previous step, so 1 plus 2 is 3. This is 1 plus 2 square 4, so this is 5, and then it is 1 plus 2 cube is 8, so it is 1.9. Again it goes back here, and this continues until the last value, the n, is attained. So this is the utility of the statement number. This sets the range up to which the repetitive job has to be performed, and this sets the range of the dummy variable. This sets the range of the dummy variable, so I runs from 1 to n, and this this signifies the range up to which the calculation has to be performed with each of the dummy variable, by each of the values of the dummy variable. Another interesting one, you can compare it with the analytical values. Analytical values, as for example, we know that it is n by 2, n plus 1, and other things are known. You may also compare this with the analytical values. Another thing, as in use of this do loop, let me calculate the sum of an AP series whose first term and common difference are given. In this case, in general, the terms of the AP series may be real, so we say this is the first term, AP series, this is first term, and this is common difference. So now ith term is a plus I minus 1 into d. This, and we need to calculate Sn is equal to sum over I is equal to 1 to n Tn, and the result is known to us, is that n by 2 2a plus n minus 1 d. This is the analytical value. This is the analytical result which can be obtained if one supplies a, d and the number of terms. But here I am trying to exploit this relation, that is, I want to calculate the sum term by term, and then I will compare it with the analytical value, and entire calculation is being done in real mode. So then A, D, N. I am naming the variable as I used in the mathematical statements. Then sum is initialized to 0.0 in real mode. In the earlier example, we calculated the sums in integer mode, so we set the initialization as is is equal to 0, not 0.0. If we put it 0.0, then a warning message will be obtained while compilation, because is is since the variable name starts with I, it is an integer variable, and here on the right hand side it is a real constant, so you cannot equate an integer with a real, so a warning message will be given during compilation. Then we use this, that is, we do a do loop. So do blank 1 2 3, this is the statement number, blank j is equal to 1, comma n. Then term, I denote term is this a plus j minus 1 star d. This is not a proper way of writing this. One should have do it better by writing float j minus 1 times d. This expression is in the real mode. So what it does, for the first j is equal to 1, the term is a, and for j is equal to 2, the term is a plus d. For j is equal to 3, the term is a plus 2d, and so on and so forth. And then s is equal to s plus term, and within these four columns I write 1, 2, 3. Then we write the relevant quantities, that is a, d, n, and sum, and then you stop it. Note that I am not going for any augmentation of the output. You do the augmentation as per your desire. So this is another example of you may do one more thing. This is the calculated sum. We may write analytical sum as we have written. It is for n, if I introduce a quantity fn is equal to float n. If n is 10, then fn is 10.0, the corresponding real number. Then we write S analytical, the analytical sum. Analytical sum means the sum that is obtained from formula. This is, you know that Sn just I have written n by 2, 2a plus n minus 1d. So we write it as 0.5 star fn for this much, then star 2.0 star a for this part, plus fn minus 1.0 star d for this part, and you must be careful about the left brackets and equal number of left and right brackets. And then you may also write a inputs, a, d, n, and write outputs. S is equal to so it gives you the term by term calculated sum as well as the analytical sum, and then stop it. This is the second example on do loops. Now I am going to some more complicated use of do loops. For example, sometimes it is required to implement two do loops simultaneously. That is called the nested do loops. How to use this do loop? Say we are to calculate NC2. So basically NC2 This is if we take n number, n is a number, say n is equal to 10, and to calculate the distinct pairs of numbers, say that if the number is denoted as 1 2 3 4 etc., the first pair is 1 2, second pair is 1 3 up to 1 10, or 1 4 etc. up to 1 10. This is of, then for 2 this is 2 3 2 4 continue, and lastly we have it is 9 10. These these sums of the terms will be equal to this. So if we want to do such a nested do loop, a precaution must be taken of this fact that if we have an outer do loop, do blank 1 blank, so sorry, 1 blank I is equal to 1 to n, and then we do use another do blank 2 blank j is equal to 1 to m, where n and m are two integers to be specified, then we must know that this loop must be completed first 2 and then 1. If that is the basic structure of do loop is that the internal do loop, this is the internal loop, it starts over here, so this line is equivalent to this line, and it ends over here. And the external loop, this is the external loop, it starts with this and ends there. So there will be no crossing. Note that no such loop should be there. There will the external, any loop, if you start any loop within a loop, the second loop or the internal loop must be completed prior to the completion of the external loop. I am going to use this concept for few simple cases. We have heard about Poincare delta notation. In 3D, Poincare, if we introduce two integers I and j, which runs from 1 2 3 in three-dimensional space, so we introduce delta ij is equal to 1 if I is equal to j and is equal to 0 if I not equal to j. We want to write a function or a Fortran program which will give you the value of the delta function. So to this we write 1 2 5 6 7 do blank statement number 1 1 blank I is equal to 1 3. Then the second loop, the j loop, do blank 22 blank j is equal to 1 3. If I equal to j, then delta, the delta function we write del as del. Else and if, and then we write first this loop has to be completed. Then stop it. Let me explain how the program works. first it takes the value of I is equal to 1. So first step, it assumes the value of I is equal to 1. Within this, it then takes the value of j is equal to first there. So within this, it assumes the value j values from 1, 2, 3. So if we consider this right statement, it will be first 1, 1, 1.0, then 1, sorry, this is for I, this is j, this is for delta. This is the first I is equal to 1. Then it assumes this loop is completed, so second loop is completed for a given value of I, that is first value of I is equal to 1. Then it starts with second value of I, that is I is equal to 2, and again j runs from 1 to 3. So this is 0.0. Lastly, this is the I is equal to 2. The external loop is for I is equal to 2. And then comes to the third value of I. This is 3, 1, 0.0, 3, 2, 0.0, 3, 3, 1.0. This is for I is equal to 3. So this is the loop, how it works. I have written this right statement explicitly over here. This is a simple program which has been used to define delta function, Kronecker delta. With this concept, I now go to calculate the NC2. So this is NC2 loop. Our aim is to first thing is read in. Then we must initialize NC2 to 0. So we write NC2 is equal to 0. I put it in integer mode because the number is integer. Then do loop, first do loop, do blank 10 blank I is equal to 1 comma, I keep it first blank because I will put it afterwards, and then do blank 20 blank j is equal to, again there is a blank. As the example I have taken, you note that the ij values were like this: 1 with n is equal to say 4, 1 2 1 3 1 4, then 2 3 2 4 3 4. These are the loops. So this I loop, I runs from 1 to this 3, which is n minus 1. So I write it is n minus 1. And j loop, the j value starts with I plus 1, the given I value plus 1. So I should write it I plus 1. So if we calculate how many terms are there, 1 2 3 4 5 6. So 6 values are there. So 4c2 is equal to 4 into 3 upon 2 into 1 is 6. So here the logic works. So we do this. NC2 is equal to NC2 plus 1. Then first 20 continue, then 10 continue, and then write This is a logic which is generally used in sorting. So if you were given a number of terms, say number of data, n data, and one need to write them either in ascending or descending order, then for a given n data there are nc2 pairs. The nc2 pairs could be done in this fashion, and the sorting logic must be implemented within this. I will come to this after some time. This is the use of do loop. In the next class I shall introduce the array variable, and we will come to the operation involving matrix addition, matrix subtraction, and matrix multiplication, where the do loop will be used extensively. So this much with the examples on do loops.